Hello, everybody. I hope you're all doing well. So my name is Patrick Sabrin, and I will be the host for this first webinar of a series of webinars that we'll be doing with Lumex Instruments. And the webinar today is how to set up a simple but yet powerful capillary zone electrophoresis method. And we're going to go right into the webinar right now. As I mentioned previously before, if you have any questions, feel free to put them in the chat, and we will follow through with the questions from you after the presentation via email. Thank you. All right, so in this webinar today, we're going to cover a brief introduction to Lumex Instruments group of companies. We're going to talk a little bit about the instrument portfolio so that you have an idea as to what we manufacture. And we're going to dive right into, after that, in the subject matter, which is setting up a capillary zone electrophoresis method. Lumex Instruments is a worldwide company and has an installed base of 1,500 instruments in 92 countries. In this map there, anything indicated in blue indicates that we have at least one instrument from Lumex Instruments installed in that country. We have several offices. Our main office is in St. Petersburg. We also have an office in Hamburg and in Beijing and in Mission, British Columbia as well, which is very close to Vancouver. Our personnel, we actually have 300 plus people working at Lumex Instruments in our various offices in Canada, Germany, Russia, and China. And most of the people that work for Lumex Instruments are highly skilled technical people. We also do have several PhDs that work with us in order to implement applications that run well with our equipment. What Lumex Instrument does actually is they do develop and produce analytical instrumentation, but they don't only stop to that. They're actually also developing techniques, analysis techniques actually, applications that run with that equipment to give a real answer to customers so that customers truly have something that they can use in order to answer to their analytical tasks. We're also responsible for training and installation of all of our equipment across the world, and we do service everything ourselves worldwide. So let's jump in now to our portfolio of instrumentation, and we have several instruments that we produce, but one of the instruments that we produce is the mercury analyzers, the RA915 models. We have the M, the F, the Light, and we're actually going to come out with the RA915 Lab. We also have a spectrometer, our fluorometer in the Fluorat O2 series, which actually deals a lot with total petroleum hydrocarbons. TPH is what we've been using it so far lately this year. Speaking of other spectrometers, we have an FTIR gamut of products. We have one that is mid-range, which is the first FTIR that you're seeing here is our FT08. This FT08 has a very large sample compartment, and it enables you to put in all the needed accessories that you would need to run FTIR. And then we have another instrument. This instrument is probably the most easiest instrument that you've ever run in your life. This NIR FT12 is what it's called. It's a near infrared system as well. And the way it works is you put your sample in a cuvette. You put the cuvette in the holder, you press go, and 90 seconds later, boom, you get your report. So consider yourself now trained on NIR. We also have a graphite furnace atomic absorption unit that we produce as well, the MGA 1000, that comes with or without an auto sampler. And this system actually maintains a very nice and steady temperature. It enables us to go to lower detection limits, and we can also have a special background correction, Zeeman background correction on this, so that we're able to go to further wavelengths. The next system that you see here is a microchip-based real-time PCR analyzer. It is the new kid on the block that we're manufacturing right now, called Ariadna, and we actually have a webinar tomorrow about this unique technology. So if you guys want to join in, it's not too late for you guys to sign up. And last but not least, the system that we'll be talking about today, the capillary electrophoresis, our Capel series. This one that you're seeing right there is the Capel-205 system, which is right here beside me as well. So let's jump in a little bit into capillary electrophoresis and why is it so attractive to certain customers. And capillary electrophoresis has been around for a long time. Most of people that are here probably know this. And the thing is that what attracts people to this technology is its unique separation power. So you can get up to millions of theoretical plates. And it actually has very low reagent. It doesn't use a lot of sample. And it actually also is very inexpensive to operate. And furthermore, it actually gives you very fast analysis. The thing is, though, is you do have to own in on the theory behind capillary electrophoresis to kind of bring all the value to what you want to get out of this technology. We've been involved in environmental analysis, food and beverage control, pharma and biochemistry, and also academia with this type of instrument. So now what I want to do is I want to jump into the types of electroseparation that exist out there. And I've actually quoted on this slide 6 types of electroseparation, which I feel kind of englobes the whole capillary electrophoresis package. And don't get me wrong, though, there could be instances where you guys might find other techniques, but you'll notice that most of the techniques that you'll find are fairly compatible with what I'm actually presenting right now. So one of the first type is capillary gel electrophoresis, and capillary gel electrophoresis is mainly used for DNA work and also proteins. We also have micellar electrokinetic capillary chromatography, which is used for things that are not typically very miscible in water. We have CEC, which is capillary electrochromatography. We have another technique called capillary isoelectrofocusing, which is a very cool technique which uses a pH gradient in order to do the separation. We also have an older technique that was used in the 70s and in the early 80s called capillary isotachophoresis. And finally, the technique that we'll be concentrating on is the capillary zone electrophoresis, which is why we're actually talking today. All right, so if we jump into capillary zone electrophoresis, and to tell you the truth, every technique that's there needs to have these type of important features. So the first thing it needs to have is we need to have a system that is able to maintain stable capillary temperature. That's very important because it enables you to go to the higher voltage values, and actually that enables you to get better separation. You also need a system that has to be adaptable to various capillary sizes because it makes it a bit more versatile when you can use different size capillaries. Typically, capillaries will be 375 microns OD, and we have an internal diameter of 50 and 75 micron, which is currently used mostly by pretty much everyone. But there are instances where they're using other types of sizes as well. We need a system that has a sensitive detection limit. And as you will see, our system is the Capel-205 is equipped for that as well. We need a system that has a robust high voltage power supply, because if you don't have that, then basically that's the heart and soul of the whole separation. So if that's not the case here, then you're probably going to have an issue with your electroseparation. You need to have a system that is capable of holding multiple samples and buffer sets. And that's actually very practical when you're doing method development. You can actually set various sets of buffers in a given system and run it overnight so that you have results the next day to know which buffer is better to use with the compounds you're trying to analyze. And finally, you need a system that is versatile. You need a system that needs to be versatile, because what I mean by versatile is that it can run all of the 6 electroseparation that I've mentioned on the previous slide. All right, so in order to kind of go through these options and basically these things that we need a system to have, what I want to do now is to show you a video of a demonstration that I'm doing. We're actually going to be running our IQ test mix in this demonstration, and this is what we're going to be using after the video to kind of own in a little bit more on the theory around capillary zone electrophoresis. So I'm actually going to stop the slides here. There we go. Perfect. And I'm going to click on video here. The video will last 35 minutes, so probably the bulk of the presentation, but stick around, look at what's going on in the video. You'll actually understand a bit more how to operate this system. And after that, I'm going to come back with more theoretical information. So here we go. And here we go. Hi guys, Patrick here, and I hope you're all doing okay, and welcome to my humble science tool shop, where today I'm going to do the demonstration of the capillary electrophoresis, the Capel Model 205 from Lumex Instruments. But just before we jump into the demonstration, I would like to show you some of the features that this system offers. So come on down, we don't have to go very far. So guys, this is the Capel-205 that I mentioned previously, and it's powering up right now. So it's going to go through its power up functions. There's a couple of things going on the software. The power button is right here, and there's some toggle switches here which I'll touch base on in a few minutes. So it basically goes through a routine where it'll actually check the signal. It'll move the trays back and forth. We can actually lift the sample compartment when it's powering on, so that actually kind of enables us to see a little bit what's going on inside. And in a few seconds here, once it's finished powering on, I'm going to show you the all the features that that need to be shown. All right, so the system's powered up, and so let's start with the features of this system. So here we have the sample carousels. We're actually going to dive in depth here a little bit closer so that you guys can see what's going on. There's an inner and an outer tray. The outer tray is the inlet side. The inner tray is the outlet side.
So there's always 2 vials at the capillary position, one inlet, one outlet. And what we do is we do pressure rinses. We'll also do voltage separation in the 2 vials. And I'll show you where the vials actually end up at the capillary so that you can see them in the up and down position. Right now, right here, this black part here is the capillary cartridge. So that's where the capillary lives. Right about in this position here, there's the capillary window, detection window. And right in this black part here, in behind that, there's the fiber optic so that we're actually able to capture the signal, the UV signal from the capillary, from the molecules that are migrating through the capillary. And we can collect signal from 190 nanometers to 400 nanometers. There's in this top part here, we're not going to see this, but there's a monochromator in here, and that's what makes this system really nice, is it's got this pretty cool feature where the monochromator actually enables you to detect stuff at a more sensitive level. And right in here we have this little drawer here, and it has a little knife. And this is used to prepare the vials that actually go into the system. So I'm just going to leave the drawer here for a second. So we use these vials from Starseed. Sarsteed. I keep messing up that name all the time. So here we go. And as you can see, the lip here is stuck to this vial. And what this little knife does in the drawer is, I'm actually going to pull this closer to you. So you push the vial right in here, this slot, and with the knife, you go ahead and you cut this little lip. And then what happens is I'm going to put this drawer back in place again. It actually separates the 2 entities. And the reason why we do this is because our system is able to decap the vials. So we actually have a decapper that pushes the top off, and you're basically able to cap these vials if you have solvents that can evaporate in your samples. Most of the time it's only water that we use, a little bit of buffer, so you can actually even use these without the caps and it'll be fine. And that's pretty much it for that part. So I'm going to bring you in closer to watch the tray. And just before I do, just note those 2 little toggle switches here are the switches that I'll be using to kind of get the tray moving back and forth. So I'll show you the tray. Alright guys, so this is the tray, and I'm going to use the toggle switches that I've mentioned earlier. And you'll notice that the tray can move from one way to the other way. So it's basically used for when you're ready to load your samples, your buffers. It makes it a little easier to do it this way. You could also do it through the software, but like I said, it's easier to do it through this way, and it makes life a little simpler for you to load your samples. You'll notice that there's a graph here indicating which way the vials should go. So of course the proper way is on this side right here indicating. So that's how the vials go in, with the predominant part towards the back of the unit. So that way the decapper can take the cap off. And then these are the vial holders that we see right here. These vial holders have a little orange O-ring, but there's 3 positions, 3 little prongs, and it's the middle prong right here that I'm pointing to that needs to sit towards the front of the unit, and that's how we would load all of these vial holders. Typically when the system comes shipped to you brand new, all these vial holders are in a pouch, so you just need to take them out of the pouch and install them in this fashion. It's pretty straightforward, really. Nothing too complicated about that. One thing that I want to mention on the tray is you'll notice here there's a position. It's kind of like a U shape. We're going to try and move in closer to it. There we go. So we're a little closer to it right here. And this position here is a special position where it actually either brings the vial to the decapper so that it's able to decap the vial, or it's actually used to trade some positions from the outlet ring to the inlet ring just in case you need additional positions for samples. And this is all done through the software, of course. And you can basically have from vial 1 to 35 on the inlet side, and then from vial 36 to 59 on the outlet side. So that's it for the tray. I'm going to show you now the capillary cassette, how to remove it, and then we'll actually look inside the cassette as well. Alright guys, so this is the capillary cartridge. Just before we go ahead and uninstall it, we have to make sure that this LED here is green. This indicates go and that we're able to take the capillary cartridge out. If the LED is red, that means there's water flowing through the capillary cartridge, and therefore we can't remove it, or else water is going to squirt out of the system, and that might create a bit of a mess, so we don't want that. There's another way that you can actually check and see if the coolant pump is off, and I'll be touching base on that for the capillary cooling reservoir, and show you how to fill it up, and you'll actually see when it's on, when it's off, if you're not too sure about the LEDs at the beginning. But like I said, if it's green, green means go, red, stop. Alright, so we've checked that our LED is green. To remove the cartridge, we lift this lever up here, and then we take this big lever down here, and then we're able to pull the cartridge out. And this is what the cartridge looks like. And actually, I'm going to show you this up close and personal in the next frame. So here we go. So as you can see, this is the capillary cartridge, so we're moving in close for a closer look. And if we start from the left-hand side all the way down to the right-hand side, so the left-hand side, you'll see two big orange O-rings, and this is the inlet part of the cartridge, and this is where we'll actually be doing our high-pressure rinses. These two O-rings ensure that everything is sealed so that we're able to do high-pressure rinses. Moving towards the right, you'll notice there are two adapters coming out that are white in color, and this is where the water coolant comes in and out of the capillary cartridge. So it's a closed circuit, and there's a pump that actually activates everything inside. And you'll actually see this once we go right towards the reservoir and take a look at how this operates. And then the last part there, that's the outlet side. And you'll notice the little wires dangling, those are the polyamide coating of the capillary. So let's move in a little bit closer into the capillary window. And you'll notice there, I've actually high magnified it with my 20x lens. This is what the capillary window looks like. So it's pretty cool. You can actually see the 75 micron capillary inside the detection window. So basically, that's the path length that you're looking into when you're doing detection. And then if we open up the capillary cartridge, you'll notice that that's the inside, and there's a lot of tubing. So the lower tubings that are connecting to the white connectors are where the liquid come in and out of the capillary. So if you see the far right connector, white connector is the inlet. It goes through the big white adapter on the left side, goes all around the big tubing on top. The big tubing on top is where the capillary is. And then from there, it comes out of there's a black holder. That's the optic holder. So that's where all the optic detection occurs, what I've shown you earlier. And then the liquid will come right out and go back into the reservoir. So that's the closed circuit. One thing as well that you have to pay attention to is the capillary total length and effective length and the inner diameter. So it's all indicated on the top part here. As you can see, it's a 53 centimeter effective length, so all the way to the detection window, and then it's a total length of 60 centimeters, and that's how you would calculate your electrical field. And it is a 75 micron capillary. So this is basically the description for the capillary. It is also indicated on the first image that I shown you as well, LEFF and LTOT. That's it for the capillary cartridge. We're going to reinstall it. So we've closed the cartridge up, but just before I go ahead and reinstall the cartridge, I just wanted to show you one last thing. This part here was what I was telling you about the fiber optic. So the capillary window that I was showing you earlier will actually match up with this part. What kind of aligns everything is that black holder for the optics part, and that's how we'll detect the signal coming off of your capillary. So it's pretty neat. And the holes that you're seeing here, this is where the inlet part of the cartridge connects. These two holes here are where the coolant will plug in so that it'll circulate through the capillary cartridge. And then where the fiber optic is, that's where the outlet part, so the right hand part of the cartridge, will reside. So just before I go ahead and install the cartridge, I'll show you one last little thing, and we're going to go ahead and install the cartridge. So this part right there that you see here with the light and everything, that's where the electrode sits, and that's the inlet side of the system. That's where the capillary will actually be coming out of, and you probably can see the little wire there that's in the bottom there. I'll actually point it out, and that's the platinum electrode that's coupled on a high voltage power supply, and that's where the voltage is applied. So that's the inlet side, and let me focus on the outlet side. So this is the outlet side that we're focusing on right now. It's a little hard to see with the video, but there would be a platinum wire there too. I'll point it out. And then, of course, this is where the outlet vial would sit. And that would complete the circuit to do the high voltage separation. So we're going to go to the next step where we're going to reinstall the cartridge. Alright, reinstallation of the cartridge. So I'm just going to bring this lever down. And as you pretty much have already guessed, what we're going to do is we're going to do the reverse of what we did earlier. So I bring the cartridge in here, just kind of push it down a little bit. Bring the arm back up and then close the arm, and that's it. Capillary is now ready to go. I'm going to show you the reservoir next, and we're going to start the coolant right after that so that I can actually show you guys what's going on in the reservoir when the fluid is circulating. Okay guys, so this is the door that you will access the capillary coolant reservoir. And this is what the capillary coolant reservoir looks like. It's about half full, as you can see right there. I'm actually going to do a quick freeze frame so that you guys can really dive into the minimum and maximum fill levels. And I'm also going to show you how to fill this reservoir. It is filled with distilled water, so makes it a very not expensive coolant. And typically you're going to fill this about once a week. It all depends on the usage and how many times you actually remove the cartridge. Okay guys, so as you can see, indicated by the lower line is the minimum fill level, and then indicated by the top line is the maximum fill level. And basically what you want to do is you want to fill it up to the maximum fill line when the pump is off, so when it's not circulating. And when it's circulating, it's about halfway that you want to fill it up. Typically, you'll look at this about once a week to see where the level is. And while the pump is pumping, you want to keep it halfway. And when the pump is stopped, you want to keep it close to the maximum fill line. And I'm going to show you how we go ahead and fill the reservoir. Okay guys, so we're going to be using this syringe right here. And the fill port is right over here. There's a little lower lock on top of it, which I can pull out. This is what it looks like. I'll leave it on top of the instrument. And then you just need to screw in the syringe in the lower lock adapter, and then you push the liquid in. And you might not be able to see this on the video, but the liquid is going up all the way to the maximum fill line. And I've put in about 30 cc's, which is what was missing in the system. Once you're done, you just need to take the syringe out. And then, of course, you can discard of the water. Re-put the little lower lock adapter back in place. And then finally close the little door for the reservoir. And that's it, you're done. I'm going to reopen the reservoir now because I want to show you guys in the next frame what happens when the pump is circulating so that you have an idea. And sometimes if you're not able to tell by the green LED, red LED, you can come and check on the side here to see if the pump is actually still pumping. So here we go. The pump is now recirculating, and as you can see, the level kind of dropped down a bit. It's not completely going to half, but basically where it's at right now is perfect. And that's it. So the system now would be ready to operate for this particular part of our demonstration. Okay? So that's it for the coolant system. And let's move on to the next step. Close the door here. There we go. Alright guys, so we've seen most of the features on the Capel-205 capillary electrophoresis from Lumex Instruments. And now we're going to jump into the demonstration part. And what we're going to be running for the demonstration is our IQ test mixture, which consists of benzyl alcohol, N-phenyletranilic acid, and benzoic acid. And it's going to be a buffer system of pH 9.2 borate buffer. So stay tuned. I'm going to go ahead and do the preparation. So we're going to jump in right into that. Alright guys, so we're going to need 7 vials in order to get our system set up for our IQ. And so pretty straightforward, as I mentioned before. We're just going to get a couple of samples prepared, a couple of buffer vials. And the first thing I like to do is when I walk in the morning to run an assay, I'll actually turn the system on. It log into the software and start the capillary coolant running because we want the temperature to be stable. This particular assay will be ran at 20 degrees Celsius, and the UV lamp will turn on automatically. And we normally like to have like a 30-minute equilibration time. So while we're preparing everything, that 30 minutes is going to go through poof, just like that. So without further ado, I've got a couple of vials here that are already cut because of my previous demos for you guys with the actual cutting tool on our system. So I'm going to start labeling these guys. So I need 2 run buffers because I'm going to be doing a water rinse in between I'm going to add 1 ml of all the reagents in each vial, except for the test mix. The test mix I can do 0.5 mils, so 500 microliters. All right, I'm going to cut the rest of these things, and I'm actually going to show you the cutting procedure again so that you kind of have a good handle of it. It's pretty straightforward, but again, it's always nice to take a look at it. So we're going to jump in, do the cutting, and then we'll come back in here and just start transferring all the liquids. All right, so the tube cutting part again. So you guys are familiar with it. I'm just going to show you the tube that we'll be using, and this part right here is what we're going to be cutting off so that the cap is not attached to the vial anymore. All right, so in order to do this is pretty straightforward. So the part that I've just shown you, that's actually what's going inside right here. You press this down and then you go ahead and cut it, and that's it. Now you've got 2 parts, as you can see, and that's how it works. So I'll finish off the rest of the vials right here. And the last one right there. Whoops, close this. Here we go. Last vial, put it straight. And that's it. So we're done. So let's go back to filling up the vials. All right, guys, so we're ready to do the transfer of all of our liquids. And I've already transferred water and sodium hydroxide in the vials. So I'm going to close the sodium hydroxide right there. One thing that I want to show you as well is I've removed all of the caps, of course, because it's a little better to put the liquid in when the caps are off. And the caps are actually going to remain off for running this IQ test because I don't really need the caps on. So nothing is going to evaporate from this. And now what I'm going to do is I'm going to transfer some buffer in my set of buffer vials. As mentioned previously, we're going to transfer 1,000 microliters, so 1 mil of liquid in each of the vials. For the reagents, so this you know how to do because you're doing this day in and day out. The thing here is that we just need to do the quick transfer. No special other thing is necessary in terms of that. As I mentioned, I've already done sodium hydroxide and water. So I'm going to go ahead and transfer my 500 microliters of test mix and adjust the pipette to 500 microliters. All right, here we go. And this is the tip for the test mix. Right here, test sample. Just shake it a little bit, make sure it's well mixed. That's it. It's my test mix vial. And here we go. So that's it for the sample transfer. So volume is about, hopefully you guys can see this in the video, is about here. I'd say 3/4 of this vial and about half when you do 500 microliters for the test mix. Okay, we're going to transfer everything onto the sample carousel. So I'll show you where we need to position everything. And we're positioning all the vials according to the program that's going to be run. And I'm going to go through the software part of it while things are going to be running, so that you guys get a grasp on what's going on and what is happening software-wise, okay? So we're going to move on to the next step, where we're going to transfer the samples into the carousel. Okay, so we're going to go ahead and load up our vials. So I'm using the toggle switch to move the vials back and forth. And the first vial I need to load up on position number 1 is the sodium hydroxide. So I'm going to go ahead and push it down there. And that's it. Sodium hydroxide is in position 1. Position 2 is water. Water in position 2. There we go. And position 3 is my rinse buffer. So again, the rinse buffer is the same thing as the separation buffer. Number 4 is separation buffer. And then vial number 5, I'll probably need to toggle the switch just a little bit more to move it closer, is our test mix. And when we do our IQ, we actually inject the test mix 4 times. The first injection will be used for a conditioning run, and then the subsequent injections 2, 3, and 4 are the injections we use to check reproducibility. Now for the outlet side, I'm going to need to load my waste in position 36, 36 and 37. So 36 is my waste. So this is my waste right here. And then 37 is my separation buffer to close the circuit. All right. If you move the tray by accident, which you probably saw me doing, when you repress the toggle key, it'll actually go and rehome itself. So no worries if you kind of slip and you let the tray slip there, it still rehomes itself. All right, so now the system is ready to go. So we're going to start the runs, and I'll show you what's going on in a few minutes on that. Alright guys, so we're going to go ahead and press run to start the demonstration. And you'll notice that the sample door is open. And this is okay right until the point where we're adding high voltage. Then this sample door needs to be closed. And I always keep the sample door open at the beginning because I want to check to make sure that my capillary is not clogged. So I'm going to show you a quick way to check that out. And it'll be happening when we're going to be doing the pressure rinses. So I'm going to go ahead and press run. And of course, everything that I'm doing here, I will show you on a snapshot of the software so that you guys understand what it is. It's actually giving me a message saying, hey, the cassette compartment door is open. Operations with HV will not start. So kind of what I just told you right away. We just click OK on that, and sure enough, it's going to go ahead. And as you can see, things are moving. Vials are coming up. And then the pressure rinses are going on. So what I want to show you is a close-up of the pressure rinses. So the little bubble that you see forming on the capillary is indicating that there's liquid flowing through the capillary, and that's a super good indication that our system is not blocked, our capillary is not blocked. That's pretty awesome. Hopefully you guys get a good look at that. You'll actually see the droplet fall off in a few seconds, and this kind of tells me, good, I know this capillary is operational. So I'm going to go ahead, guys, and close the door now that I know that everything is operational. And we'll let the system run. And as I mentioned, while the system is running, I'll show you guys a little bit what happened when we were setting up stuff with the software. And then...
All right, guys, so thank you for listening to the video. I hope you enjoyed it. It's actually a very good presentation to the next segue of the webinar here. So let me restart my presentation where we left off at the demo video. So we're going to move into the next slide here. And I've mentioned what the test mix compounds were. So in the slide here with the pKa of 14.36 is benzyl alcohol. The middle compound is N-phenylentrenoic acid with a pKa of 5.28, and benzoic acid at the end there with a pKa of 4.19. Now, the reasons why I'm mentioning this is another element when you're doing a capillary zone electrophoresis method, is you need to own in on these properties, and you need to kind of know this in order to kind of basically choose what you're going to be using for buffers, capillaries, etc. So in the test mix, we are using a bare fused silica capillary, 75 micron IED, and we're also using a borate buffer at pH 9.2. So be aware of that, because those are going to be elements that we're going to build on. So what I'm showing you right now is, because we haven't seen it, part 2 will be covering the software, and you'll actually see this coming live on part 2, which I've actually stuck the links if you want to register for part 2 in December. And it's showing us what the electrophoregram looks like of the test mix. And you'll see that benzyl alcohol comes in first, is detected first, then N-phenylentrenoic acid, and the last peak that's detected is benzoic acid. So let's check a couple of things as to why they are coming out in this order. This slide is just to show you when we do an installation qualification, we actually do look at statistics. And what we want to look at is relative standard deviation under the area percent, and then the migration time as well. So this run indicates that the test that I ran that day, everything is way below 1%. So that's excellent. That means that the capillary is performing really well, and so is the system as well. So here we go. I've mentioned briefly that we were using normal polarity, and a lot of the systems actually use the same nomenclature, but just in case, sometimes they're using different nomenclatures. There's a lot of systems out there. Just so that you know, normal polarity means that the inlet side of the capillary, where the sample is injected, the inlet side would be the positive electrode, and then the outlet side, where the sample comes out of the capillary, will be the negative electrode. And as you've seen in the video demo that I was showing you, the detector is situated near the outlet side. So we're using the long end of the capillary, So I said it was a total length of 60 centimeters. So we're using that long end, which is 53 centimeters on the 60 centimeter capillary, to do the separation. And then, of course, the residual 7 centimeters go back into the buffer vial that's on the outlet side. Reverse polarity, not too complicated. You're basically just reversing the electrodes. So the negative electrode then becomes on the inlet side, and the positive electrode now goes on the outlet side. So just be aware that for now we're using normal polarity. Another thing that I like to look at, and this is a little chart that I've built for myself because it kind of gives me a real ballpark figure as to what the residual charges are for the compounds that I'm trying to separate. And the relationship in this chart is that with the pH or the PI or pKa, like I said, this is very rudimentary, okay? But it gives you a really good starting point as to what to expect as a charge for the particular molecule or compound that you're looking at. So here the relationship is if the pH is higher than your PI or pKa, in this instance it'll be pKa, then your net charge will be negative. And of course, this is the case for this particular system that we're using. So if I jump into the next slide, I've got the little chart here. The pH for borate buffer I told you earlier is 9.2. So that means that our N-phenyl enteroylic acid and our benzoic acids are negatively charged because their pKa is respectively 5.28 and 4.19. The benzyl alcohol will remain a neutral charge molecule. So there's no charge at all here. So it's what we call a neutral marker. It is listed as having a pKa of 14.36, but the constant of dissociation for alcohols is very, very hard. So you need to have harsh conditions in order to ionize alcohols, typically. So we said that we're in normal polarity, positive electrode, negative electrode on the outlet side, and the detector is on the outlet side. We've also said that the N-phenyl enteroylic acid and the benzoic acid are negatively charged. So typically, negatively charged compounds will tend to want to migrate towards the positive electrode because opposites attracts, and of course same charge there's a repulsion there. But that's not what's happening here in this separation. So why is that? And most of you probably know this, but it's something along the lines that we call electroosmotic flow. So again, I was just showing you the regular polarity that we're using, and this is the slide I want to get to, which is electroosmotic flow. So electroosmotic flow is another piece of the puzzle that we need to grasp in order to start building a very good capillary zone electrophoresis method. And I have a quick little video here that kind of captures what electroosmotic flow is, and what I'm going to do is I'm going to stop the slideshow here. This video is like 30 seconds. I'm actually going to keep the sound on of my mic to kind of comment what's going on. Here we go. Okay, so what you're seeing here is a cute little baby girl, and she's actually speaking to her mom, and she's on an airport walkway, and she's trying to grab the drink for her mom, but the walkway is kind of pushing her away. And if some of you know what electroosmotic flow is, you probably know where I'm getting with this. So typically, she's never going to really reach that drink, and she does fall a little bit, but no worries. She's okay. No harm done. And as you saw, her dad was in behind her as well. So let me get back to my presentation here and kind of go through my point. So electroosmotic flow here, the role of electroosmotic flow in this video is played by the airport walkway. Basically, a walkway is going to carry anyone from one end to the other end of the walkway. And electroosmotic flow pretty much does the same thing inside the capillary. So what happens is that we're using a borate buffer that I mentioned at pH 9.2. And the silane oil groups that are in the capillary walls have a pKa of 6.2. So according to my little graph that I've shown you earlier, we'll expect to see them negatively charged. So what happens is there's negative charges that accumulate on the capillary walls of the bare fused silica. Now, once we rinse everything with buffer, we've reconditioned our capillary, then we've rinsed it with the separation buffer. We haven't applied any voltage just yet, but there's some sort of dissipation that occurs, and you'll start to see the positive ions from the buffer that will start to create a layer near the capillary wall because they are attracted by the negative charge of the capillary walls. So that's what happens right there, and this is what you're seeing in this image here. After that, we apply high voltage. Just before we applied high voltage, we'll inject our sample. And in our case, our sample has 2 negatively charged compounds and 1 neutral compound. So then we apply high voltage, and all of a sudden, this electroosmotic flow starts moving. And its electrophoretic mobility at pH 9.2 is very, very strong. So it basically sweeps everything that's inside the capillary all the way to the detector window. So what happens with the 3 compounds that we have is the following. Our neutral compound basically doesn't have any charge, so it's just standing there and moving slowly across with the EOF string. So basically, that's why we're seeing the uncharged compound coming out first. It's moving with electroosmotic flow. The second and third compounds, we're seeing N-phenyletranilic acid as the second peak that comes out, and its electrophoretic mobility is a little bit less than benzoic acid, which has a pKa of 4.19. So therefore, it is fighting to go towards the positive electrode, but eventually it will sweep the N-phenyletranilic acid out of the capillary. It will get detected, and eventually the benzoic acid, which will be swept out as well, and it would get detected. So when you have EOF, the order of which the molecules or compounds that you're looking at will come out will be positive charge first, neutral, and then negative charge. And that's pretty much a very simplified way to present electroosmotic flow, which I think it kind of makes it stick in your mind, and it makes it a little bit more, how should I put it, relatable. So again, this is just to show you the order of which the peaks are coming out. And that's the results we got from our IQ test mix. All right, so in summary, to have a very robust capillary zone electrophoresis method, we need to know what is the pKa or the PI of the compound of interest. So we basically need to know this information. We need to know then what's the pH of my buffer. Once we know the pKa or the PIs, we can play with the buffer combination and see what's the best buffer combination that will give us a great separation. You have to ask yourself, do I have any EOF at that particular pH? So a rule of thumb is if you start getting at a pH 4 and higher, you're starting to get a little bit of electroosmotic flow. Once you pass pH 6.2, the electroosmotic flow goes higher exponentially. So you will have strong EOF then above pH 6.2. Then after that, another question you need to ask yourself is, which polarity should I use, reverse or normal polarity? So it depends again on what you're separating, what the net charge is, and where you want them to go. So of course, you always want them to go to the detector window because that's where you'll see the peaks. There's also buffer concentration, and I haven't really mentioned that neither in the presentation or even in my slides, but buffer concentration is very important because the higher the buffer concentration you have, the better separation you'll get. However, there's a balancing act here, because what happens is basically if you're too high of a concentration in your buffer, what you're going to do is you're going to kill the high voltage, because you're going to have what we call a current leak. So remember, this instrument goes at 30,000 volts, but is very low current in there. So roughly in the ballpark of 100 to 300 microamps. And last but not least is the temperature of the capillary. I spent a lot of time on the video showing you the water cooling system. It is very important because that's what enables you to go to the higher voltages and the higher buffer concentrations. If you can maintain the internal temperature of that capillary cold, then you're pretty much going to be able to go to higher voltages and higher buffer concentrations, thus having a much better separation. All right, I've got one more element to show you, and then we'll be done with the webinar. And it's a case study that I've done this summer, actually, for a customer that was asking me, can we separate the peptides by using CE? And I was looking around the web to find a peptide mixture, and I found what you're seeing here is a peptide mixture. It has 5 peptides in there, and those peptides actually are from Sigma Aldrich. And the run you're seeing right now is this is an HPLC run. They basically everything is coming out roughly around a little bit before 50 minutes. It's a TFA 0.06% acetonitrile gradient that's being run here at 1 mil a minute, detected at 220 nanometers. So I said, okay, let's try this out using all the little rules that I've shown you, and let's see what we can do on capillary electrophoresis. So here's the next slide. And you'll see that, great, I was able to do the separation of the 5 peptides using capillary electrophoresis. But the cool thing is I was able to do it where all the peaks are coming out before 16 minutes. So can you imagine? That's like really great. We're winning a lot of time here. And also, we're using what I was showing you in the video, those vials that are not so expensive to use. And we're using milliliters of buffer and nanoliters of sample to have this great separation. So imagine how much you could save as a cost by just switching to capillary electrophoresis. So I'm really happy about the separation that I got here. This was ran this summer, and I actually use a PBS background electrolyte to get the separation at pH 3.0 using a 75 micron ID capillary. And that's it. So I hope you guys really enjoyed the webinar. I know I'm really happy I was able to present this to you.